All right, so this video is to go over the warm-up today, which also is a review of what we did last class. So we started talking about our t-test that coincided with our t-intervals. So we did our t-intervals and our t-test anytime we were given a mean and a standard deviation. We talked about that there was two types of t-test, a one-sample t-test and a two-sample t-test that we're going to run in this unit. So if I look at the three examples in the warm-up, a shoe store manager claims that the average cost of a pair of tennis shoes is $89.95. So this is the initial claim that we're testing this against. So since this is our initial claim, that makes our mu not, right, 89.95. This is the initial value that we're testing everything against from there. So then we made a sample or ran an experiment to collect data ourselves that we can test against this initial claim. So the sample we had was of 68 pairs of shoes. So that's going to make N68. And our average cost, so that's the same thing as mean. Our mean was $90.26, and our standard deviation was $3. Test the managers with a significance level of 0.05. So that comes in down here. That critical value or significance level here for us is 0.05. So because we're given a mean and a standard deviation, we're running a t-test. We only have one sample to go off of, so it's just a one sample t-test. So then if we talk about the conditions of our t-test, so remember the conditions that we have to follow is that it's a simple random sample. Our other condition, yes, we said we did, we're assuming it's a simple random sample, that our n value is greater than or equal to 30. So we have 68, so since that's greater than or equal to 30, we're good there. And then our third condition is that our n value is independent of the population. So if you think about, it is reasonable to say there is more than 680 pairs of shoes out there that could be part of this test. So then we're testing that the claim is that the average cost of shoes is $89.95. So that would be our words. The average cost of shoes So in this case, that would be, right, our null hypothesis is always represents equality. So equals, we always have an equals in our null hypothesis, so that our mean is $89.95, and that is our claim, right? The average cost is $89.95. So then our alternative hypothesis is that it is not $89.95, right? Because our claim was the null hypothesis, we take the opposite for our alternative hypothesis. So then once we have this stuff written down, we're able to run our test. So we're going to get our calculators. We're going to go stat over to test. Yes, we hit the stat button, arrow over to test, and then we're doing number 2, which is the t-test. And then we're going to input this data that we had from the problem. So our initial value is $89.95. Our mean is $90.26. Our standard deviation was 3. And we had 68 that we were comparing it to. Our alternative hypothesis is that it's not equals. So we'll select this one and then hit calculate. So we get that our t value is 0.8521. And then our p value, which you can see on our calculator, is 0.3972. So 0.3972. Remember, if your p-value is low, you reject. If it's not, if it's greater than, right, this is greater than this significance level, so we're going to fail to reject the null hypothesis. So that means we're going to keep this and support our claim. So we can say there is not enough evidence. No, sorry, there is sufficient evidence to support our claim, right? We went with this one, so we're supporting our claim. So there's sufficient evidence to support the claim that the average cost of shoes is $89.95. So then what would we recommend to the manager? Nothing. The claim he's not we're saying that the claim he's making is legit. We're not concerned about it. So I would say he's fine. His claim seems somewhat accurate. Right? If we rejected it, we would say that you can't claim that. That's not true, but we stuck with the claim that the average cost is about $89.95. All right, so let's go ahead and look at number 2. This is the warm-up that's on page, sorry, I should have said this before, 157. So we'll turn over to page 158 to do our work, to do the next one. So a study was conducted on retention of students in class who were on their phone and not on their phone. Students were taught a series of information and then asked to repeat what they just heard. How many items they correctly repeated back was recorded. Assume the samples are independent and randomly selected from normally distributed populations. Test the claim that retention goes down when students use their phone. Use a significance level of 0.05. So we can put that in here. So we are testing two populations against each other, people who use their phone and people who don't use their phone and use their phone. So this is going to be a 2-sample t-test. So all of our known values are really given to us here, right? Our n value is 15 and 11. Our means, 5.26, 3.15, and our standard deviation, 0.75 and 0.3. So those are the key information that we need to run our test. So when we check our conditions, we need to check our conditions for both categories. So we're looking at, right, we did a study, which means that we can assume this was a simple random sample for both categories. Then our n values are not greater than 30, but it says randomly selected from normally distributed populations. One of the conditions was that it's okay if it's not greater than 30, that it's normally distributed. So we're okay with it being less than 30 because it's normally distributed for both sets of data. And then if we compare those n values, I have 150 and 110. It's safe to assume there are more than 150 and 110 students who could be on their phone or not on their phone. So we feel good about running our tests based off of our conditions. So we are testing the claim. Test the claim that retention goes down when students use their phone. Goes down when students use their phone. So our null hypothesis would be that our population rate we'll use without our phone is mu1, with the phone is mu2, that they're equal, that their retention is equal. And then if we think that retention goes down when they use their phone, then we would expect mu1 to be greater than mu2, right? It's asking you to repeat what they heard. So the amount that they repeat correctly would be greater for mu1 than it is for mu2. And this is our claim. Right, retention goes down, this value is less than this value. All right, so let's go ahead and run our 2-sample t-test. So I'm going to come over here, I'm going to hit stat, go over to test. I'm running a 2-sample t-test. And so then I'm going to input the data that I have up here. So for my x1, I have 5.26, standard deviation 0.75, n value is 15. x2, I have 3.15, standard deviation 0.3, n value 11, and then I'm saying that mu2 is less than mu1. Keep the pooled at no, and then we hit calculate. So our t value here is 9.872, and then our p value It always gets into that glare at that point in the screen. Our p-value is 2.543 e to the negative 9. What that means is I'm going to move this decimal 9 places to the left, and that would be filled in with 0. So there's going to be 8 zeros before my 2543. So this number is significantly lower than our critical value. So when our p is low, we reject our null hypothesis. So we are going to reject this, right? We're rejecting the null. It does not mean that we're rejecting the claim. We're rejecting our null hypothesis. So this is not true, which actually means that we have enough evidence to support our claim because we rejected the null hypothesis. So there's sufficient evidence to support the claim that retention goes down when students use their phone. Okay, so hopefully that was enough of a review for you. However, if you feel like you need extra support, we'll go over one more together. I encourage you to pause the video, try that last example on page 159 on your own. But if you don't feel comfortable, because this is kind of different than the ones we've been looking at, we will go over it together. So we talked about this a little bit in class. This is not a different type of test. This is still a t-test because we're going to look at the differences here. The only data that we're actually going to look at is the differences in these people's scores. So it is actually still going to be a t-test, but because we're looking at a before and after of one person, it's still only one sample. We're just comparing their before and after scores. So to do this, yes, we can type our data into our calculator and find all of the values that we need. However, our calculator also can nicely store that data to run our test. So what I'm going to do is type in my difference, right? We're only going to pay attention to the difference here. I'm going to go stat, I'm going to hit stat and then edit, and I'm going to type these numbers into list 1. So I've got, let me clear. So I typed my data into list 1. I'm going to hold off on what to do with that for now. All of my values, everything I'm going to need is going to show up after I run the test, so I don't really need to figure out the values or the variables. If I want to know them, remember you can always hit stat calc and 1var stats, and it will tell you your mean, your standard deviation, your n value. So you can find that as well, but your calculator is also nice enough to run the test with the data stored in our list. So the following table shows the weight of 12 people before and after following a workout plan for 2 months. Use a significance level of 0.05, so I can fill that in at the bottom, and test the claim that the weights were less after the workout plan. So you want their values, right? You want their difference to be less than 0. Assume the samples were randomly chosen from a normally distributed population. So, our conditions, is it a simple random sample? It says they were randomly chosen, so yes. We want to know if our n value is greater than or equal to 30. We do not have 30 subjects. Remember, we only have 12. However, this does say it's normally distributed, so that can account for this condition here. And then for our next one, our n value, right, we have 12, so it's safe to assume that it is reasonable to assume there are more than 120 people that we could have used this that were participating in a workout plan of some sort that we could have used in this study. Okay, so we're testing the claim that the weights were less after the workout plan. This is where it kind of gets confusing. We wanted their weights to go down, but when we do the before and after and find the difference, right, when I subtract, I get a positive 4. This does not mean their weight went up by 4. It means their weight went down by 4, but we're not using a negative value. So we actually, right, all these people who have positive numbers, they lost weight. So we want our mean and our standard deviation and stuff to be greater than 0, because that means they lost weight. Negative numbers actually means they gained weight in this case. So you have to be really careful about how we look at the data. So in our study, our claim, right, that they weigh less would mean that the difference would be greater than 0 because they lost weight. Right, in our case, because losing weight is a positive number, we want our value to be greater than 0. We want it to be a positive number. So our mu value is always equality, so we would say that it equals 0, that there is no difference. And then our mu being greater than 0 is our claim. So then we'll go ahead and run our test. So like I said, the nice thing is we don't need all of this information because our calculator is going to have it stored for us. So if I go to my t-test, instead of stats and typing it in, again, you could have written down the mean standard deviation and typed this in yourself, would have given you the same results. But you can also go over to data, and then it can pull from list 1 all of the data that you need. The only thing you have to fix here is this initial value, and that's going to be our 0. So we'll make that 0. We want all the data to come from list 1, and then we want to test the claim that it is greater than that value. So greater than 0. So we get that our statistic is 3.088, and our p-value is 0.005. So since that p-value is lower than our significance level or lower than our critical value, we're going to reject the null hypothesis, which means there's enough evidence to support our claim that this is helping people lose weight. And you don't have to have the same thing down here verbatim as me. You can write whatever makes sense to you. A lot of the times we copy the claim, which is totally fine here if you wanted to do that. But as long as it makes sense in the context of the problem, you can kind of word that however you want. So can the company claim that their diet is effective in people losing weight? Yes, we've supported the claim that they will lose weight. So we could say yes here. All right, so hopefully this is a good review of the test that we ran yesterday as we get started on today's lesson.